Okay, hello class. So this is the second video in section 2.4. In the previous video, I basically explained what a partial derivative, actually not what it is, but just how to find a partial derivative of a function with respect to a variable. Turns out it's the same as finding the regular derivative. You just treat every other variable as a constant. So the reason why I went over that, as I mentioned, is because we're going to have to use it for one of the theorems we're going to be discussing. Okay. Now, it won't be in this theorem, it'll be in the next one, but they're both kind of telling you the same thing. Just one theorem is going to be more general than the other one. So let's start with this theorem. So consider the first order linear. So we're specifying that it's linear ODE. We know that a first order linear ODE is going to have this form. Why? Well, you start with something that looks like a1 of x, y prime, plus a naught of x, y equals, say, h of x. So this is the general form of a first order linear ODE. Divide everything by a sub 1, so we get y prime plus a naught of x divided by a1 of x, y equals h of x divided by a1. And then what you can do is you can think of a naught divided by a1 as just being a function p of x. And then h divided by a1 is just being some function g. Right. So you can always rewrite a first order linear ODE in this form here. Just divide by whatever's in front of y, of the first derivative. Now, notice that this is a first order linear ODE. Not only that, it's an initial value problem because I'm also giving you this initial condition, that y of x naught equals y naught. So this first order linear differential equation with this initial condition is an initial value problem. That's how we defined it in the previous videos. So given this first order linear ODE and this initial condition, what we're going to ask is there a way for us to guarantee that a solution exists? So again, without actually trying to solve this differential equation, so without actually trying to find a solution, can we, just looking at this, guarantee that a solution exists? And that is what this theorem is going to say. So if p of x, so whatever expression of x is in front of y, and g of x, whatever doesn't have any y's, right? And right now it's written on the other side of the differential of the equation of the equal sign. If p of x and g of x are continuous on some open interval around x, that contains the input for the initial condition, then as long as that's true, that's the only condition we're going to have, that p of x and g of x are continuous in some open interval containing x naught. As long as that's the case, that there exists a solution, and not only does it exist, but it is unique. So there exists a solution, a unique solution for this differential equation defined on this interval I that we found. So this is very powerful because, again, I mentioned in the previous video the importance of why it's important to know whether a problem has a solution and whether it's unique. And here, given this problem, it's an initial value problem, there's a very easy condition that we have to check to know whether this problem has a solution, and in fact, that it's unique. All you have to check is that p of x and g of x are continuous on some interval containing x naught. As long as you have that, you're guaranteed that a solution exists inside whatever interval you found. So that's what the theorem says. Now let's actually use it in an example. Now let me mention something about the numbering here. So I'm following the notes that I used last summer, and since the lectures were longer, I was just dividing my numberings into lectures. So because now the classes start a little bit shorter because I'm doing everything online, what I'm going to do is I'm going to just label my numberings per section, right? So I'm in section 2.4. I'm going to start the labeling of the examples again with example 1. So I'm sorry about that. So there's going to be a little bit of me having to scratch out some numbers, but hopefully it's better, because I think if I don't do this, it's going to end up being like example 40 or example 50 or something like that, and we don't want to, That'd be a little bit confusing later in terms of finding the examples. So I'm just going to relabel every time I'm starting a new section. Okay. So let's go ahead and use theorem 1. So use theorem 1 to find an interval in which the solution to this particular initial value problem exists. So we have an initial value problem. We have a first order ODE, and we have an initial condition. So by definition, that's an initial value problem. So that's the differential equation. That's the initial condition. First of all, in order for us to use theorem 1, notice that the condition is that it's a linear differential equation. That's one restriction that we have. Right? So in fact, there's two conditions. Right? These conditions that are mentioned here, and the fact that the differential equation has to be linear. So before we use this theorem, the first thing we have to check is this differential equation actually linear? So let's just check that real quick. So we have, again, what was the process to check whether something is linear? Find the derivatives and look at the coefficient in front. Here we have y prime. So whatever's in front should be an expression only involving constants and the independent variable t. Okay, t minus 3 satisfies that, so that works. There's another derivative here, like y to the 0th derivative. So whatever's in front of it should be an expression only involving t's and constants. Okay, the natural log of t only involves t, so that works. Finally, look at everything that's not multiplied by a derivative of y. And again, this has to be an expression only involving t's or constants. Okay, 2t satisfies that. So this is linear. Just a linear differential equation, a first order linear differential equation. So we can apply this theorem. The first thing is, notice that this theorem here, let me just erase some things just so it looks more clear. Just erase some of these things. Yeah, just that. So notice, first of all, that this theorem assumes that our differential equation is in this form. Right? Basically, we divide it by whatever was in front of the first derivative. Right? And I mentioned how you can always do that here. You can always divide by whatever is in front of the first derivative. So before we start doing anything, since we need it to be precisely in this form, we're going to first rewrite our differential equation like this. Okay? So take whatever's in front of the first derivative and divide everything by that. Okay? So if I do that, what do I get? I get y prime plus ln of t divided by t minus 3 times y equals 2t divided by t minus 3. Right? So since we're dividing the left-hand side of the equation, we'll also have to divide the right-hand side. So that's the first thing you want to do. Make sure that your differential equation is in this right form, where you've divided by whatever is in front of the first derivative. Okay. So we checked it's linear. We put it in the right form. Now, in terms of the theorem, what matters is the function in front of y and the function that's not multiplied by any derivatives of y. So what I like to do is always label those in my differential equation. So for our purposes, whatever's in front of y, which in this case is ln of t divided by t minus 3, that would be our p of t. That would be our p. You see that matches our p there. And whatever is not multiplied by a derivative of y, that would be our g of t. Now that we know what p and g are, we have to check the condition. Right? So if p and g are continuous on some open interval containing the input of the initial condition. So let's find such an interval. Let's find an interval, an open interval, for which p of t and g of t are continuous and that contains the input of the initial condition. So for our purposes, x naught here is equal to 1. So the x naught being talked about here is the input, which for our case is 1. So we want to find an open interval that contains x naught equals 1 and for which p of t and g of t are continuous. So let's find at what intervals are p and g continuous. So first of all, let's look at the domain of p of t. So p of t equals ln of t divided by t minus 3. Since there's a natural log there, you know that the domain of natural log is all t values greater than 0. So for sure, our domain is restricted by that. Okay. So the domain here is at least restricted by t being greater than 0. So domain restricted by t having to be greater than 0. Now we also have another domain restriction. We can't divide by 0. Actually, let me do that in another color. So we can't divide by 0. So t minus 3 can't be equal to 0. Okay, so when is t minus 3 equal to 0? When t equals 3. So not only does t have to be greater than 0, but also t cannot be equal to 3. Now those are the only domain restrictions, and in fact, on this domain that we've defined, this function is continuous. Well, how do you know it's continuous? You can draw the graph. So what is the graph going to look like? Well, I can't draw it off the top of my head, but it's going to look like some continuous graph. And at t equals 3, there's going to be a hole, like a dot. Remember from college algebra, you kind of draw it with an open dot. But other than that, the function is continuous everywhere else. Okay. So another way you can determine whether a function is continuous in an interval is you can take the derivative, right? And wherever the derivative exists, your function is continuous. And that just comes from Calc 1, where differentiability implies continuity. But here, the domain ends up being the t greater than 0, can't include 3, and our function p of t is continuous on this domain. Again, that's something you should have learned in Calc 1. I told you a couple of ways you can determine that, whether it's continuous. I'm just going to assume that you know how to determine it. But if you don't, try to think about some of the things I said. The domain is this, and p of t is continuous in this domain. Now let's do the same thing for g of t. Okay, so g of t is 2t divided by t minus 3. Oh, and actually, let me rephrase something I said. If you draw this graph here, it's not going to have an open dot. In fact, it's going to have a vertical asymptote. It would have an open dot if you could cancel the t minus 3. But since you can't, it has a vertical asymptote. And I realized that because I realized that's the same thing that happens here. So if we look at this function, what's the only thing restricting the domain? Well, it's the fact that we're dividing again by t minus 3. That's the only restriction. So in this case, the domain is just not including 3. So actually everything not including 3. So I don't necessarily have to start at 3. That's 0. Negative infinity to 3 union 3 to infinity. And again, you can take the derivative, you can graph it and see what it looks like, but you should see that not only that, but g of t is continuous in this domain. Now, what were we looking for? We're looking for an open interval in which both p and g are continuous, and that contains our input for the initial condition, which was x equals 1. So looking at these domains, can you find an interval, an open interval, on which both p and g are continuous and that contains t equals 1? So I think I said x before, just because of the previous example, but working with t, so let's just call it t naught. Yeah, so this is important. Notation is important in mathematics. So I try to use the best notation in my notes. It's definitely easier if I'm working with the whiteboard. Right now I'm working with the tablet, so the amount of space I have to write in is less, but I'm still trying to keep the best notation as I can, because I do require you to use correct notation, so I should be using correct notation as well. So going to the problem again, find a open interval for which p and g are continuous and that contains t equals 1. Okay. Well, let's see what the intervals of continuity for each function is. Well, we can't use this open interval because it doesn't contain t equals 1. Remember, it has to contain the input of the initial condition. Right? So the same, we can't use this interval for that. We could use the interval negative infinity to 3. That interval certainly contains t equals 1. The problem is p is not continuous on that whole interval. P is only continuous on the sub-interval that goes from 0 to 3, not negative infinity to 3. So what interval can we use? Well, we can use the interval I equals 0 to 3. You can check both P and G are continuous on this interval. And not only that, it contains t equals 1. Now, of course, this problem has infinitely many solutions because all you need is an interval containing, for which both these functions are continuous, that contains t equals 1. You could use smaller intervals than this, right? You could use 1/2 to 3/2 and get smaller and smaller and smaller. But as a note here, in general, as a general thought, you want to use the largest such interval. And of course, in practice, if you're trying to find an interval for which a solution to a differential equation exists, it makes sense that you want to use the largest interval possible, right? That gives you more room to work with. Okay? So in general, you want to use the largest interval possible for this theorem and the next theorem we're going to cover. And for any theorem like this, we're going to see other ones. Okay, so what does this mean? We found an interval for which theorem 1 guarantees that a solution exists, and not only exists, but is unique. So we know that, let me write it, by theorem 1. And if you were doing this like as a homework problem, I would want you to write something like this as a conclusion. Right? So by theorem 1, we know that a unique solution exists for this initial value problem defined on this interval that we found. And that's how you use this theorem. Again, now if someone wanted to find what the actual what the actual solution is, well, now it makes sense to look for it because we know it exists. And once they find such solution, they don't have to worry about whether there are other solutions. They know that it's the only one. So again, that's how you use this theorem. Check that you have a first order linear ODE. Again, this only works for linear ODEs. Once you have that, oh, didn't want to erase that. Well, that's what it is. So once you have that, rewrite your first order linear differential equation in this form. Find what P and G are. So once you wrote it in this form, whatever's in front of Y is P, whatever's by itself is G. And then find an interval in which both P of G are continuous and that contains the input of the initial condition. That's all you have to do. You're guaranteed that on that interval, a unique solution for the initial value problem exists. And again, if you want to know how to do that, go back to this example here. One example is really enough because they're all like the same. So I might ask you a problem like this in the homework, but it's basically going to be the same thing. Just rewrite the differential equation, make sure it's linear, find P, find G, find the interval containing the initial condition. And again, try to always find the largest one, okay? The largest such interval. Okay, so that's all for this theorem. In the next video, we're going to talk about a similar theorem where we don't require the differential equation to be linear. So since we're not requiring it to be linear, as I mentioned before, the fact that the differential equation is linear lets us use techniques from linear algebra, so they're easier to work with. So you'll see in the next theorem, if we don't require the differential equation to be linear, we still have a similar theorem as this. We can guarantee a unique solution to an initial value problem, but the way to check or the way to find that interval like we did here, well, it's going to be a little bit more work.